In this video, we're going to look at the second part of the reaction rate lab, and primarily we're going to look at the calculations. The big part is this whole big box on page 2. So I'm going to model some of the calculations for mixture 1, and then you can carry that out for the rest of them, and then we'll use that to do some other problem solving right here. So I think I'm going to grab a marker or maybe a spotlight right here to start out. So here's just a repeat of data from the first page. In mixture 1, we had 10 milliliters of Ki, which was A, 5 milliliters of B, 10 milliliters of C, or these different substances right here. Everything was done about 20 degrees Celsius, and this one took 25 seconds. And how did I get the concentration of I minus to be 0.080? So in order to do that, I realized the formula is Ki, it's in a 1-to-1 ratio. And I also realized I started with, Isaac, thanks. I just realized I started with 0.20 molar Ki. So what's going to happen is I'm going to dilute this. So I could do this a couple ways. I could take 0.2 molar times my number of liters. Okay, so I convert this to liters, and then that would give me moles, and then divide it by the total liters. Well, doing the same thing in this more simplified step is to say, hey, if I have 10 milliliters of this solution A or Ki and 15 milliliters of other stuff, it's 10 out of the 25 milliliters was solution A. So essentially 10/25 or 2/5 of it was 0.20 molar. So I'm just going to take 0.20 times 10 over 25, which would be my dilution factor. And it's the same effect as multiplying by the liters and dividing by the total liters to get to that substance. So maybe just modeling that right here, I could write that in, and yeah, I think this works okay right here. I'm going to write this in and say it was 0.200 molar, and then it would be, and I think it was, just looking at my figures on that, 0.20 molar, sorry, 2 figures, times, and I said I had 10 of A, but I had 25 total milliliters because I had 5 of B and 10 of C. So I said 0.20 times 10 over 25, and that's going to equal my 0.80 molar. Okay, so that's going to be the first one. What's going to happen when you do, if you have 7.5 here instead? Well, if it's 7.5 over 25, 7.5 is 3/4 of 10. I'm guessing this answer will be 3/4 of 10. So you'll see it'll be quite systematic in your results right there. Okay, the next one I'm going to look at is the concentration of S2O3 minus 1. And I'm going to do the same type of thinking. Notice that one is really dilute. And it's kind of the trick behind the whole reaction mechanism and that turning blue color. But anyway, I look at this, and this is 0.0050 molar by itself. But in reaction 1, I have 5 of this B, and I have 10 and 10 of the other. So 5 out of 25 milliliters are the 0.0050. So this is how I would do this calculation. You go down and find this here. That's pretty good. And let's do this. 0.005. Oops, I didn't get that in. Try again. 0.0050 times 5 over 25, and that's what equals the 0.0010. So that's what I did. I did that dilution factor. And then for the last one, I could go back to the other page. I don't think I'm going to do that, but it was not 0.2 molar to start with, it was 0.1 molar. So I'm going to take 0.10, and I'm going to multiply that by 10 over 25, because there were 10 milliliters out of the 25 milliliters, and that's going to equal what, it's going to be half as much as 0.8, so that's going to be 0.40. So you're going to get kind of a big web of calculations. Probably should have put a molarity in there, but it does say in molarity, so I think you see the big M right there. So that's how I got these molarities right here. And how would I get the natural log? Well, just do it on your calculator. Natural log of 0.080 is this, the natural log of this. And these are in between things. Technically, I guess we'd have two figures, but sometimes with the in between data, I like to carry extra figures, and then I can always round back at the end. Okay, so I think we could get this. We didn't really care about, we're not plotting B or this solution at all, but we're kind of looking at A and C, but we're just kind of figuring that out as we go. Okay, the next step is, what about this reaction rate? So we could, do we want to measure it in A or B or C right here? Which one do you think would be best? And how this reaction mechanism works, it actually gets defined when something happens to B. Actually, we see the color change when B runs out. So I think it makes most sense to look at it in terms of this. So that's why I'm choosing to do that. And in order to solve for this, all I did was I took this 0.00, let's see, this 0.0010 and divided it by the 25 seconds. So I looked at this change and I knew it completely went away. So by saying it completely went away, then I know I didn't have anything left. And when we learn more about the reaction mechanism, that might make a little bit more sense. So I'm just going to write this in here, how I got this one, and that was 0.0010, and I'm dividing that by 25 seconds, and that equals that really small number, 4.0 times 10, and I know this isn't like an exponent, but I think you can see it with what I'm working with here, 4.0 times 10 to the negative fifth. Okay, so that tells me the rate of this B in this reaction. And we can kind of see how the B ends up going away in this reaction. So that's why I chose that one right there. Now, where did I get this 4.0 times 10 to the negative fifth, 2.0 times 10 to the negative fifth? When we look at the next part, we're going to actually look at the mole ratios in the equation, and it's a 2 to 2 to 1 ratio. So for every 2 of these that react, 2 of these, and then it's 1 of these. So once I figured it out here, I just went through the ratios here. So if you figure this out, this is going to be the same. This is going to be half as much, the one below it. So that gets us close to the different things you need to do. The last one is figuring out the rate law, and that's kind of the big piece here. So we're going to assume this is the right rate law. It might seem to fit some of the data we talk about later. It might seem contrary to some of the data that we talk about, but process the data and do that, and we'll come back and talk about the whys in class. But if this were the case, then K would be rate over I minus times S2O3. And where are you going to get that? Well, here's I minus right here, the 0.08. And for reaction 1, where's the S2O3? It's 0.040. Where is the rate? Where is the rate? The rate is going to be this one that we determined right here, the 4.0 times 10 to the negative fifth. So to model that reaction here, I'm going to dump these other ones and clear this out. And to model this rate here, I will say, or I model the determination of K. I'm going to say K equals, so K equals, and then I'm going to say the rate, which we said was this one right up here, 4.0 times 10 to the negative fifth. And that's going to be, and again, that would be an exponent, -5, and then divide that by the two concentrations. One would be 0.08 for the I minus. In the other one, and we said that's the first power, and the other one would be 0.040. I don't want to do that. So we'll just leave it like that. I try to put another 0 in that. I want this to go to another spot. Okay, so I put a 0 on there and a comma. That's not going to help much. So I take this over this and this, and ultimately, I'll try this. Oops. Okay, got a little space in there. And then that's going to equal, I think I got 0.0125. And I probably round that to 0.013 if I were worried about the sig figs, but you see that. See if you get consistent results for your case for all these other things. If you do, you probably have everything right. If you don't, there's probably one thing, it might just be one mistake, and that's what we'd have to work through as you work through these calculations. So that's the calculation box for mixture one. Follow that model for the other ones. And let's take a look at where we're going to go after that. The other parts of this lab is just looking at the graphs. I really graphed everything for you. And you see 0th, 1st, and 2nd order. There's a couple questions. And then that's for A. And I did 0, 1st, and 2nd order for C. There's a couple questions there. And then I spun this on its head and asked us to think about it more like one of the differential rate law box and ask you some questions with that. So that's ultimately what we're going to be trying to piece together. So fill out the box, try those other pieces, and we'll see where your questions are. Okay, thank you for watching this, and we'll have one more with reaction mechanisms.